there anything new from yesterday, or did we cover like everything that's going to be?
You know, if you want to just maybe work on paper now, maybe that would be better. Want to do that?
Just on these?
Yeah.
Yeah. Yes.
I mean, I think it would still be good if you guys really could work together.
Yeah. Yeah.
On paper. But we sort of done the demo problems for online people. We need to fill it all.
Yeah.
So this way you can actually make progress on your homework less time to spend on doing stuff. We can maybe focus on things that might be the most interesting. So we did this one. This is very similar. This is one practice. This is practice.
I didn't finish only the last part.
Did you finish?
So we did something?
Yeah, yesterday. That was the last long sheet.
Is it goal 75? Oh yeah, that's 75. I don't know which one it is. 75.
Yeah, the one. Yeah.
And this is where I think you're on. So both of them are related. So actually 76 is pretty easy. So yeah, maybe just start working. Just go through all. I don't think, I think this is sort of a little bit interesting. There's a couple here that have some interesting concepts. Really, it's all the same. So what I kind of was thinking is maybe in order to, because if you do them all on the board, you still have to write them all down to turn them in again. So why don't you just work on paper now? And I will print out more copies for you guys and just start going through those. And I still recommend you work with a partner. So maybe Isaac and Savneet, you can work together, and or maybe Isaac and Jose Savneet. Matthew can work together. Okay. Well, maybe Alareza will come and they can work together.
It's not only 0. Because I didn't include the equals 4, 8, 18. I didn't include that. I didn't even solve it. Yeah.
What's the answer?
I didn't answer that.
I didn't heard that.
Well, once you get the X, the Y, and the Z, when you do that, Y,
So what I was thinking, I don't know what you guys think. I mean, if you want to do it on the board, you find that helpful, you can do that. But then I was thinking maybe at this point, we filmed the core one, so now you can sort of do it on paper, and then you don't have to do it all over again. Because you still got to turn in something on. That's all good?
Yeah.
Maybe this is not a really good place to kind of work together. Table. But maybe maybe what you could do is like the three of you guys can sort of sit at the end and slide this over. Want to do that? I'd like to kind of have you still have dialoguing. That's a long time working these through, but rather than wasting time, like I really don't know how to solve this. I still don't know how to solve this. In 5 minutes, I have no idea. So that you can have a conversation and kind of work through. This is basically how engineers get through engineering school. Sorry, what? What about big leagues? Yeah, it is, because you can't figure it out by yourself. Nobody can. You actually have to work in a team. Yeah, why don't you get that?
speak up.
Maybe
it's on the pretty good.
Yeah, you guys can move. There's more copies of this.
What's the problem?
Yeah. Yes, I got nothing. Yeah. Same here.
Wait.
No, I said,
No, I got it. I took it last week.
Yeah, so there's a question about, on the first one, how do you understand or how you interpret the, the direction of rotation? It's pretty clear that F1 is going to cause a counterclockwise rotation of that beam about 0.0, and what you're calling F1, which is sort of oriented along this axis, and you call it F2. So your F2 is kind of oriented along this axis. It's maybe not be so clear which way F2 is causing things to rotate, right? But realizing that your fulcrum or your axis is right here at O. What I tell people is to think of like a water wheel. So if there was a water wheel right at O, which way would the vane spin if this force F2 hits it? It too is going to make it go this way, right? Yeah. So if it's traveling to the left above the axis, it's going to make things go counterclockwise. If it's below, it's going to make things go clockwise. And another point on this problem is you could kind of make more sense of it if. Oh yeah, that's a really old eraser. That's okay. I was just going to erase some of this stuff here. Is to, you know, in many situations they give you a problem that's sort of crooked or whatever, and you already sort of figured that out, but you can clarify what you're doing by saying, well, you know what, I'm going to make this my y-axis and this my x-axis. Maybe it comes out of O. So that way you can go back to calling, instead of F1, you could call this Fy, and instead of F2, you can call it Fx, which kind of helps, I think, keep things a little straight. Yeah. Thank you. Today we are doing more in-class problem solving, so guys are working together. And if a question gets elevated to where they can't figure it out themselves, then they'll come up here and I'll record it for online folks.
Thanks.
So here you have a problem where you have to find Fx. And in this case, the axes are aligned vertically and horizontally, right? So it's really just the horizontal projection of F, right? You already know how to do that.
Yeah.
What is it?
Sorry, what is what?
Well, your question is how do you find F1, right?
No. How do you know if it's counterclockwise or it's clockwise?
Oh, if the rotation is counterclockwise or
Yeah.
clockwise? Well, again, you imagine F, this is the principle of transmissibility. The force can be applied anywhere along the line, its line of direction. So in other words, you could apply the force here, but if there was like a bracket sticking up here, you could also apply it here, and it would have the same effect on the body.
Because it's clockwise? It's counterclockwise.
Which way does that, when this arrow, if the wind is blowing this way,
Oh,
and you have a fan or whether, yeah, it's going to be going rotate that way. Yeah. It's very simple.
Yeah.
No insights yet?
Not so far.
It's all pretty straightforward, right?
Yes.
I drew it like this. So since it's this whole thing, right, is being pulled up at the y-axis by this force,
Yeah.
which is 150. So since it's counterclockwise, that's why I put positive. And then this one over here, which should be the same as this one, is being pulled by that component, like that. Right? So that's why I put it here. So that's the way that I thought about it in my head.
That's exactly right. Yeah.
It's just a
And-
little confusing.
And well, it also explains why, if this was, because these will actually, as this gets more and more kind of tilted towards O, the net moment gets reduced more and more because these start to cancel each other out. Like the moment that wants to make to go this way from this component is going to sort of cancel out the moment that wants to make to go this way from this component, right?
Right. So
And
then
as this
similarly-
line goes straight towards O, then they exactly balance out and the net moment is 0. Yeah.
So what's the deal with like having the negative sign like here?
Well, that's how we keep track of how they add together.
Okay. But I mean, like when you multiply that, there's no negative sign.
Well, my instruction on the sign is to not worry about how the components contribute.
Okay.
A lot of people want to have
Yeah.
symbols in there and they don't want to think about the sign. They want it to just come out of the computation.
Yeah.
You're usually going to make a mistake if you try to do that.
Yeah.
So the way to make it so it doesn't make a mistake is to not worry about the sign when you're doing the multiplication. And then at the end, look at the number and then ask yourself, is this component making this thing want to spin clockwise
Yeah,
in case it's
exactly.
negative, or counterclockwise in case it's positive?
That depends on the component.
That's all you do. Just don't try to make the sign kind of work out algebraically because you'll never get it to work right. It's really, you have to look at the problem and just sort of, it's by inspection, really. You can tell by inspection the way the sign is
So
going
that's
to
why these problems are in this type of course, because if this were to continue to increase, then it'd be in equilibrium. Is that what you mean? So
No, I
that
was
turns
saying
into
is
like a
if
static
the angle, if the direction of F changed so that it was intersecting, the line extending from F would intersect O exactly.
like this.
Yeah. So if the angle is a little bit less, right now it's 30, but if it was like say 28 or 27 or something, then it'd be perfectly aligned with O. In that case, the vertical component, you're still creating a moment that's counterclockwise, and the horizontal component is still creating a moment that's clockwise, but then when you add them together, they add up to 0.
So what you're trying to say is that if this increases, this angle's going to be smaller.
No. I'm not talking about anything increasing. I'm just saying if the direction of F got changed so that this was like, say, 27 degrees or something, and now it's coming straight out of O, that's why there's no net moment, right? There's no moment arm, right?
Right.
And you can also prove it by these components, right? Because now the vertical component, which wants to make it go this way, would exactly cancel the horizontal component, which wants to make it go that way.
Yeah. That's interesting.
So why is the y component negative if it's pointing to make it go clockwise?
The y component has a moment that's going to be counterclockwise, so that should be a positive moment.
Right.
What are you calling MO1? I don't know what MO1 is.
That's the y here.
Okay. So if MO1 is Fy times,
Oh wait.
so you got to keep, so the 0.612, D2 is the moment arm for Fy.
You know.
I don't know what the unit is.
I think I'm just getting my numbers mixed up.
Yeah, you can easily put the wrong D on the forces and then you get really wrong answers too. So you have to be really careful about this. In fact, I would just say, the moment of the force, you could say, okay, MO equals, you can use symbols here, right? You can say, well, it's Fy times D2. This will help you straighten things out, right?
Yeah.
It's Fy times D2,
Right, the
and that's
equation.
positive, right? And then it's F2 times, you haven't labeled D1, oh, there's D1. And it's F2 times D1. And then, you write these things out, and then you look at each one. Well, is Fy times D2, is that going to make things go clockwise or counterclockwise? Look at Fy. Fy kind of, pulling up right here. Again, you can apply that Fy anywhere along its line of action. And so you can imagine this is a big water wheel, right? And if this thing is pushing up on a water wheel, which way is the water wheel going to turn around O?
Mm-hmm.
Clockwise, so that's positive.
I mixed up my components, so it's
Yeah,
multiplying
it's easy to
D2
do.
times.
And F2D1, again, hitting that same water wheel, but now it's coming from the left and moving to the right. Which way is the water wheel going to turn?
Yeah.
Clockwise, right? So there's a minus there.
The way I looked at it, like to figure out if it's going counterclockwise or clockwise, is I would look at like when you're looking at the y components, the line of action is like horizontal, and the x components is here. So like when it's horizontal, if you look at just the y, then it's going to go that way. But the other way, it goes the other way because you're looking at like.
What you just said, I cannot parse.
No.
Yeah. Try to say it again with less words.
Hmm. Like when I was considering
Yeah.
the f of x for the direction,
Yeah.
I actually looked at the vertical line, like relative to it,
Why?
because that way you can see like it's going that way, and then
Wait. You can see it's going that way. What do you mean by what's it? And
the direction.
you mean the rotational
Yes.
force is trying to go that. So when you're looking at fx, right?
Mhm.
Fx.
Yeah.
Okay. You start to think about the vertical component.
Yeah.
Okay. That really doesn't have anything to do with it. The vertical component of f doesn't have anything to do with fx or the moment.
I mean, I got the right answer though when I looked at it.
You know what? You have a 50% chance of getting the right answer. But over time, if you don't really
Yeah.
understand it, you're not going to get that right all the time.
Okay.
Okay, so it all comes down to how is this force going to make this body spin
Mm-hmm.
about O?
How far can you get?
It doesn't matter if there's a vertical force or not.
Mm-hmm.
If it was completely flat, how would that force make this pipe spin about O? And
The x.
yeah, this X force.
Well, yeah, then it's clockwise.
It's clockwise.
Yeah.
Good.
And then
Which is going to be, we're going to call it negative.
so clockwise is negative.
Yeah, just for
Okay, that's what I
convention.
thought.
What is, Tom, I get the whole process, but what does this number mean at the very end?
The very end. Do
Yeah, like what is the value of MO? Like what is that?
you know what a torque wrench is? Have you ever worked on cars?
No.
Really?
I know it is.
Are you a mechanical? You're a civil engineer. Okay. What's a torque wrench?
It measures the torque.
Well,
You can torque things to appropriate torque.
yeah, a lot of the bolts in an engine are specs that you can only apply so much twisting force to it.
Oh, okay, gotcha.
So a torque wrench has a lever on it, and then it
Yeah.
has a wire that's not connected to the wrench, so it's calibrated to kind of bend.
Mhm.
And then there's a scale on there to indicate how much twisting force you're putting on the bolt. If you put too much, the bolt breaks off. And then you swear, and then you got to go find a way to remove the screw from the hole without a head on it. And torque wrenches are supposed to keep that from happening
Because they tell you.
because they tell you when you're going, and you have to look up the spec for each bolt that you're working
Yeah.
on in an engine block, because that really is annoying when that happens. That's the twisting force. That's a torque.
Right.
Okay.
Huh.
Hurricane Irma is a big torque.
Basically, son.
A tornado is a big torque.
Mother Nature's
It's a rotational force.
Right. So that's true.
Yeah. Irma doesn't move very fast, but the winds are whipping it like, 150 miles an hour. But the speed of the storm is really, really slow.
Yeah, like the net speed of like the actual like the whole like.
Yeah.
So then that number is pretty much signify the moment, the movement.
It's signifying a rotational force. A moment is a rotational force.
Okay, gotcha. So it's just how.
How much tendency of that is there to make that thing want to spin?
Okay.
And if this object is going to be in equilibrium, then not only do the vertical and horizontal forces have to be in equilibrium, but also the rotational forces have to be in equilibrium. Because if they're not, then the
it's
thing's
just
going to spin.
move.
So later on, we're going to be doing systems of equations that involve, when we look at rigid body systems, we have to not only check that the forces all add to zero, but also the rotational forces add to zero. These are the moments.
Oh,
That's
I
what we're
got you.
How is
I
moment
understand
different
what it
from torque
is, yeah.
in
It's the same
definition?
thing.
It's just
It's just another word for the same
But
thing.
isn't
The moment
torque,
and the
isn't
torque.
torque force?
Yeah, a torque is a rotational force. That's what a moment is.
But you said the MO is in the perpendicular
Pardon me?
direction, right?
What?
You said that MO is in the perpendicular direction. of rotation?
Well, between work and moment is the work is force times distance along the line of force. Right?
Yeah.
A torque or a
Plug
moment
it back in.
is force times distance, but the distance is perpendicular to the force. It doesn't have to move. A moment doesn't require anything to move.
So even though
It's still the moment.
moment is force times distance, it still is like considered like a similar.
It has the same unit as work, but it
It's the
means
same
something
unit.
completely different. Work is like energy.
Yeah.
And things have to move to have work.
Yeah, exactly.
But
Yeah, we were
moments,
talking
they don't have to move at all.
Because it's not. Yeah. Okay.
You
'cause
can
this
apply a
open's
twisting force to a
perpendicular.
screw or a jar. You can, you try to open, next time you try to open up a jar, think about how much moment you're applying to it. That's a torque. The jar's not sliding left or right. You're holding it in place. There's no net force, but you are causing a twisting force to get that to open.
And that's the moment.
That's a moment.
Oh, I see. Gotcha. I understand the differences now. That's funny.
Yeah.
Who would have thought?
So how do you not differentiate? How do you like? What's like the difference between moment and torque? Or you said that's
It's the same thing.
It's the same thing.
Yeah. Some books call them torques, some books call them moments.
Okay.
Oh, okay. Same.
Generally, engineers call them moments.
Yeah.
Probably mechanics call them torques.
Yeah.
I don't know.
How would they do that?
Physicists call them moments too.
Jesus.
I don't know. But sometimes in Europe they call them, who knows? In Britain they might call them.
But it is the same thing.
Yeah.
Moment. Okay. It's good to know.
Yeah. That's why you're doing all this stuff. And that's why they're looking at these rigid bodies. So in order for this thing not to actually spin, and this is, I can kind of give you a little preview, right? This thing is being supported by this bracket which is screwed into the wall.
So there's a lot of force on this.
In order for this thing not to just drop, right, because of this force pulling on it to try to make it,
Yeah, I'm gonna try and solve.
I don't know which way the net moment is on this thing. I think it's a net moment of negative, right? Is the net moment clockwise on this thing?
Counterclockwise.
It is counterclockwise?
Yeah.
Oh, I'm sorry. So the line of action is going below. Yeah, so it's actually trying to make it go that way.
Yeah.
Well, then, if you also add in the fact that there's a weight on here, the weight of this thing is also making it try to go that way.
Right.
Well, whatever is not balanced between the weight of this thing causing a torque and this thing causing a torque going the other direction has to be sucked up by this bracket. Otherwise, the whole thing is going to break or fall or twist off in one way or the other.
So there's like bolts that.
So those bolts are also applying a moment. And guess what kind of moment they're applying? In a way. Well, they're kind of like, there's a couple there.
Oh yeah, that there's like 6 bolts or whatever.
Yeah, one of them's, the top ones are actually, if there was no force here, like if it was just the weight of this thing,
Yeah.
I was rotating this way, then this would be applying a couple to counter that.
Right.
And the top bolts would be holding it in, and the bottom bolts aren't doing anything. It's just the brackets getting a normal force from the wall to push it out. And that provides a counter rotation to keep everything balanced.
Are you gonna later on figure out how to?
Yeah, like next chapter.
Okay.
But we're going to play around with this stuff for another week.
Okay, good.
Yeah.
Yeah, that's good.
We're going to be looking at moments in 3 dimensions, and then how to reduce complex systems of forces and moments so that they're simplified so they're easier to work with.
Oh, I got you.
So you said that the bolts on the top of the bracket would hold it up.
Yeah, if it was just
Or
like
hold it
well, like,
from
if you have,
falling.
that's like a cantilever, like if you have a balcony or something,
Uh-huh.
and, it's against the wall, here's the wall.
Mhm.
It may go into the wall a little bit. You
Yes.
never really know how those things are actually rigged up. Or maybe there's some bolts here holding it in to something stronger. But if it was just just like a board, stuck in even like a diving board, just a board stuck in there, right?
Oh,
Well, you can imagine what's happening is if it does start to drop a little bit, right, what's going to happen? Well, the back of the board's going to hit like this corner of the slot, right? And the wall is going to be pushing down on it because, if it wants to twist this way, and the bottom is going to be pushing up right there, right, to hold the thing up. Well, that, again, you have sort of a moment here that's causing a counter rotation this way. So if the board doesn't fall, it's because of the structure providing a support. And these are called reactions. Those are reactions of the structure on the body.
and you said next year we're gonna figure out the counter forces, right?
Yeah, we're gonna have to figure out all these reactions because when you design something, you got to make sure that it's going to be stable.
And then
So
again,
the reaction forces have to be met. They have to meet the load forces that are trying to make it spin the other way. And you have to design like these brackets and stuff, all these mounts and stuff. As an engineer, if you're a structural engineer, you got to be able to spec these things so that they can handle all the load that they're going to get. You have to understand the load right there. It's a really important part of that thing.
so then in this problem, since it's SS 36.7, you would say joules counterclockwise.
Not joules.
Or
Newton meters.
That's a unit of energy.
yeah, Newton
That's
meters,
for work.
Yeah. Newton meters.
It's always going to be
Um,
Newton meters. Yeah.
Counterclockwise, then right here.
Yeah.
The opposite rotation, of course, would be negative 36.7.
Yeah, you have to balance that out.
Right. And then.
Yep.
Okay, gotcha.
Mhm.
That makes sense.
Good.
Just drop it off with your coworkers if you're gonna change it.
Any questions over here?
That's it.
All right.
Yeah, I do. I got a question. About 4-7.
Uh-huh.
So what we started with was just breaking this down to the X and Y,
Yep.
and then just defining what the value of like 4 kilonewtons sine theta for the
Mhm.
Fy, and then 4 kilonewtons cosine theta,
Mhm.
and we put our distances in and everything. So we set up this equation kind of.
Yep.
Plugged in this, found out what these are,
Yep.
all together multiplied, and we got all this. But we
Uh-huh.
have it in sine and cosine.
Yeah.
So since those are two variables, is there an easier way to do this?
I think you're gonna have to just guess those. That's a real guess and check.
Okay.
Just iterate. You can guess and because it's a transcendental equation. You can't really solve
Yeah, you
that.
can't really do it.
Yeah, there's no trig formula to reduce that as far as I know.
Okay.
But you can plug in a bunch of numbers. However, I'd like you to go back and look at this thing and realize, did you check the sign of these?
Oh
components?
no, yeah, okay, yeah.
The SIGN,
that.
yeah. So I think you're going to want to redo that.
Okay.
Well, I mean, I think there's an SIGN issue.
Okay.
You guys got to run because if you want, there's nothing coming in here. I'm going to go, but you see how effective it is when you're working with people that are, as opposed to doing it all by yourself.
Yeah.
So this is what the stem cell stuff will eventually allow you to do too. Yeah, it's due Monday.